So when we shoot that footage in RAW, like I said, this is all the information off the sensor, and we haven't processed it in any way, shape, or form. One of the big things that we make a choice about is what is the color temperature for this whole scene. Now, color temperature is basically measured in a temperature scale called Kelvin. And we talked about this a little bit already when we were talking about the monitors, but basically what happens is there's this thing called a black body radiator. Okay, well, let's back up for a second. First of all, every single light is coming from a filament, right? Basically. So all our light sources are going to come from some sort of filament, right? So that filament is obviously a physical thing that then has electricity applied to it, and the atoms, molecules vibrate at a certain frequency, and then we're creating light here, right? So with that in mind, or obviously light can come from chemical reactions as well, like burning and things of that nature. But right now we're talking about our standard light bulb. So in the case of that, basically everything's going to come from some sort of filament. So that in mind, how it works is we have this piece of metal that is the filament that then gets excited or heated up, and then we start obviously creating light. So with respect to this temperature scale, there's this thing called a black body radiator. This black body radiator is basically heated up, and as it heats up, it emits light. And it emits light through a specific range of colors. So we go back to here. Here's what I'm looking for here. So basically, you'll see this curve here. So this is our color space. So this would represent visible color, basically. And then these smaller triangles represent our color spaces, like a WRGB, an sRGB, or whatever. And this curve right here basically represents Kelvin temperature scale through this color space. So as our black body radiator heats up, it becomes red, and then it becomes orange, and then it becomes white hot, and then it starts going into this blue range here. So that means that light created from any filament is going to fall somewhere along this curve. So from a filament, you're never going to get green light, for example, or you're never going to get magenta or whatever. So if you're looking directly at the filament, yes, you could put something in front of this, like a white light, this green piece of glass, and you get green light. But we're talking about light being created directly from the filament, right? So with that in mind, like I said, this black body radiator heats up, and then we get this scale of temperature, and that temperature scale is called Kelvin. So if you take a look at it, take a look at the Kelvin temperature scale, you'll see that basically your candlelight, things of that nature are going to be here. Daylight is going to be right around 5,000, 5,500 K, and as you go up here, you get into these cooler lights. So in the past, basically what we had when we shot film is we pretty much had film at two temperatures. So, if we have, once again, we have the scale here. And you can see at the bottom, we're starting at about 1,000 Kelvin, which is like your candlelight, and you're going up to like 10,000 K or something like that. So, like I said, there were two sort of points in here that became important for us in terms of photography. 3,200 K and somewhere around 5,000 K. 5,000 or 5,500 K. Why was that? Well, basically, in the past, when you had film, you had 3,200 K or 5,000 K film. 3,200 K was referred to as indoor film, and 5,000 K would be our outdoor film. And basically, what I'm saying that we have 5,000 K or 3,200 K is what we're saying that 5,000 K is neutral for that film, or 3,200 K is neutral for that film. So what that meant is that if I had a light, like this light, for example, here, if that was 3,200 K, if I exposed it with this piece of film, it would look white or neutral. Similarly, if I was outside and I exposed something that was underneath the sun, which is basically right around here, daylight's right around 5,000 K, then that would look neutral. Okay? But what happened if I took this outdoor film inside and this indoor film outside? Well, as we go down here, we're getting warmer. As we go up here, we're getting cooler. So basically, if I expose a 3,200 K light source with 5,000 K film, it would be very, very warm. Similarly, if I went outdoors and basically expose sunlight with this 3,200 K film, then neutral is up here. It's at 5,000 K. So we're basically going to offset the color in one direction or the other. So it basically creates the point that there are two issues. There are two issues. There's the issue of what are we considering neutral in the scene, and then what are the color temperatures of each light. So, for us, normally we don't change neutrality. 5,000 K is basically neutral for us in terms of our vision. That's basically white, right? But that doesn't have to be the case digitally. So, for example, if I take a color meter and I hold it up here and I determine that that light is, say, whatever, that's probably like about, it's probably around 3,000, somewhere around there, right? So I say that that light's 3,000 K, right? Now, it depends on it depends on, if I want that light to be warm, if I determine that that light's 3,000 K, if I want that light to be warm, then I can basically set my neutral level up here, and everything under that is going to be warm, right? But if I set my neutral level at 3,200 K, then that's going to be white. But if I want that light to be cool, then I set my neutral level down here, and then it's going to be, anything above our neutral level is going to be warm, and anything below our neutral level is going to be cool. Or sorry, the other way. Anything above our neutral level is going to be cool, and anything below is going to be warm. Right? So, the thing that you can do when you're processing your raw images is, first of all, you set color temperature for the whole picture, the whole image, basically. So you're determining what is neutral, and so you're setting that position. Okay? So you can see that, basically, if you look at this, so let's say that's 5,000 K, that's 3,000 K, and let's say that's 6,500 K. So that gives me like neutral, cool, and warm, right? But if I say 3,000 K is neutral, then that gives me cooler and cooler, basically. So that becomes white, that becomes bluer, and that becomes even bluer. Or I could basically say 6,500 K is neutral, that becomes white, then that becomes warm, and that becomes even warmer, right? So the point being is that, like I said, there's two issues. There's what is the color temperature of the individual light source, and then what are we saying is neutral for the whole scene. Okay? Does everyone understand that? Okay. And the best example of actually seeing like real world lights at different color temperatures is kind of cheesy, but it's automotive lighting. So basically, something like this is probably good. So if you look at, ignore all this other stuff that's going on. If you look at this picture, you can see that, somewhere around here is going to be neutral. Anything underneath here is going to be warmer, and anything above here is cooler. This light is this color because the actual filament is creating light at 30,000 K. It's not because it's a white light that has a blue lens in front of it, or a white light that has a yellow lens in front of it. It's because the actual filament coming out of this HID lamp is actually creating light at that color temperature.
Question is the color measurement saying which light is brighter, or is it?
It has nothing to do with brightness. It has only to do with color.
Okay, that's the question.
Yeah. So like here's another good example, I guess.
So blue light can be just as bright as the red light.
Yeah, it has nothing to do with brightness or intensity. All this has to do is color of the light. So you can see this is warmer, neutral, and then cool, and then these very purplish colors. So you can see this is the same thing. It's just kind of showing general Kelvin. Like I said, 5,500 is right about at the center. So you can see how warm those 3,000 K lights are. The 5,000 K should be pretty neutral for us, and then the high ones go to really cool colors. Okay, so you can compare right.
So what does that mean for someone who works in lab?
Well, it's possible, it depends on how you're lighting, but it's possible with mental ray to actually work all in color temperatures like that. So,
but as far as just putting a spotlight in the scene and like picking a color.
Yeah, see, by default, you're not working like this. You're not thinking about this as a color temperature environment. You're just, like you said, picking a color, basically, just randomly doing something. Whereas it's possible in mental ray to actually there is a black body radiator node that you can actually feed into light, so you can actually determine, you can basically tell it exactly what color temperature it is. So it's possible to work scientifically or in more of a real world scenario than just like randomly. Okay? Any questions about this?
If the Kelvin of the sun is 5,000,
Yeah.
how could the color of the clouds be higher? Because I was just seeing like candles, and sun, and then refer back to like clouds.
Well, because there's a lot, like, that becomes cooler because of the effect of reflected light in the atmosphere, basically. It changes the wavelength of the light as opposed to direct light.
I actually don't know how to explain it.
Yeah.
Basically, the light works in like the additive way of mixing. So you're actually using blue, red, and yellow being mixed into a white color. Yeah. And what happens is the atmosphere, like the sky, is not really blue. It just seems that way because the blue vibration is smaller than the others. So it gets like scattered over the place in the atmosphere. And what you're getting when like the light that we get is the red and the yellow coming in. which is why it looks warm, but it's not green. Like you're getting the red and yellow light, but the blue is being spent.
Yeah, I mean, when we see any color, it's because that surface is basically absorbing the rays except for that, whatever it is, blue or red or whatever else.
Right. What are those crazy little hologram things that you like twist around and they?
Well, what about them? How do they work?
Yeah.
It's the same idea. It basically you know, a hologram is created by basically interference between two lasers. So they actually they take a beam splitter and they have your three-dimensional object and it basically takes that and projects that. And so when you have interference, it creates a different pattern of interference on a piece of holographic film. And then the level of interference, I guess, causes that sense of depth, basically. And then but holograms aren't like color accurate, really, because that's why you get all that. It has something to do with the emulsion of the film. That's why you get all that weird, funky. They always come up with like a rainbow a little bit, you know, because the emulsion is not set up so you get like direct color representation, right? However that works. So. Okay, so let's talk about another topic in lighting that's important, which is basically when we do get to lighting stuff, when we do get to lighting stuff, we're going to need to think about things in terms of the key to the fill ratio. So, in its simplest form of three-point lighting, we have our subject, whatever that happens to be, and then our primary light that's shining on that subject is going to be referred to as our key light, right? So we're going to have our key light, and that's going to be our primary source of illumination. Now, that is going to be balanced against our fill light, and so we're going to, once again, have some sort of dynamic range from the highlight to the shadow. And that's going to create this thing that we're going to refer to as the key to fill ratio. Now, there are two extremes here. These images would be referred to as high key images. And it's kind of a little bit confusing, basically. But basically, a high key image is an image that has a low key to fill ratio. So when we have a ratio of 2 to 1, we're saying the key light is twice as bright as the fill light, basically, or 4 to 1 or whatever. So these ranges here would be referred to as high key. Now, the opposite of this, and if you take a look at this, you can see that if you look at the dynamic range, from the highlight to the shadow, there's not a lot of tonality change. Now, this particular one has a lot more saturation in terms of color, and his hair actually is black, or his shirt is black, so there's some darker things in the scene. But you can see her eyes are black. There's a black in that scene as well. If you look at the light, highlight the shadow, there's not a lot of dynamic range. Similarly, if you look here, if you look at the highlight areas, which is kind of like, his nose is a little bit specular, but if you look at the areas that are illuminating and not reflecting, if you take a look at that, and then you look at the shadow, there is no shadow, basically. I mean, if you look at his face, there's some, occluded areas or whatever, but there is no, dark cast shadow anywhere, really. So, this would also still be a high key image. Now, the opposite of this would be, the direct opposite of this would be low key lighting, which has a really high key to fill ratio. So, and you can see that these are obviously images that it's 100% key, almost no fill, right? So, so you get this like film noir kind of look, or the chiaroscuro look that was popularized by Caravaggio, and you get this like super high contrast look. So your high key lighting is going to be something like that, very flat, and your low key lighting is going to be like super contrasty like this. Okay? And so when people are designing lighting schemes, oftentimes they're going to look at the intensity of the key to fill and talk about things in terms of these ratios. Now these are the extremes, like this 2:1 or the 16:1. Most things are going to be somewhere in between most normal lighting scenarios, right? So most normal lighting scenarios are going to be somewhere in between. Like you would never go below 2:1 almost. Like 2:1 is almost like is in terms of high key lighting as far as you would go. And on the other side, 16:1 is pretty crazy. Like 8:1 is pretty hard. So most things are going to be somewhere in between there, more like 4 or 5:1, something like that.
So is that like a 1-to-1? Like it would be just
1:1 is completely flat. Yeah, key and the fill are equal. Yeah. So you would never really go there, or you'd have even less definition than you have like an image like that. It just starts going very flat. Okay. Any questions about that?
That almost looks like, if you scroll back up, the image on the right almost looks like a video game.
This one.
Yeah.
Yeah, well, he has, he's being lit with two large, well, it's actually one large softbox. You can tell actually both of these are being lit with a really large softbox. This one's even bigger. You can always tell if you look at his eyes. See, that's a really large softbox with the photographer standing in the middle of it. Yeah.
It really reminds me of like how in video games they love to really punch like the normal maps and make everything really great looking, and because they don't have like real time like actual lighting.
Well, I mean, you can see this image has depth of field, right? Because if you look at his face is in focus, and the focus is dropping off to his ears, so there's a pretty shallow depth of field there. It's pretty saturated, obviously. There's a fair amount of color in here, and you can see it's sharpened quite a bit. There's like obviously no retouching, and it has a lot of micro contrast or sharpening, so it feels like what you're kind of like really gritty, like his pores are coming out and all that kind of stuff. And this doesn't make him look pretty,
And yet they love doing that in video games.
Yeah. Well, it's got that grungy sort of feel. It looks really odd, actually. Like, if you really look at it, like, see how underneath his eyes are, like, white almost? Like, so there's a white underneath his eyes. It's very odd. It's almost like and his lips are, like, kind of, like, oversaturated. And it's because they're pushing the saturation quite a bit.
It looks like he came out of heavy rain.
Yeah. Okay, so that's the end of this. This is our like basic discussion here. So I know we talked about a lot of stuff, but all this stuff is important here. So let's we're about 2:48. So let's take a break, and we'll come back and actually get on the computer and do a few things.